It is Tuesday, November 17th, 2020, and today we're going to be looking at probability rules. A little bit more about how to determine probability, different tools we have. If you're taking notes, you have a notebook or anything, you should have that ready. There will be some new things to write down. All right, so first we're going to look at probability models. Probability relies on the fact that chance behavior becomes predictable over many repetitions in the long run. Fortunately, there are ways we can determine probability of a particular outcome without repeating a chance process over and over again. So there's another tool we can use besides running simulations or doing that process hundreds and hundreds of times. Right? We don't want probability to take forever all the time. We need other resources. Right? To do this, we use what's called a probability model. Right? This is a list of all possible outcomes. We call that a sample space. We use the letter S to represent that sample space, and a probability of each outcome. This is the definition straight from the textbook. So we have their definition of sample space and probability model. The sample space S of a chance process is the set of all possible outcomes. This could be a list of all the possible outcomes. It could be a table of the possible outcomes. It could be a picture of all the possible outcomes. It's just a sample space. A probability model is a description of some chance process that consists of two parts, sample space S and a probability for each outcome. Okay, so we'll look at a example of this. But first, can you raise your hand if you would like a moment to write anything down from this slide? Let's try that again. Sample spaces, right? Sample spaces can be very simple or very complex. For example, in tossing a coin, there are two possible outcomes, heads or tails. We can represent this sample space with the notation S equals H, comma, T. So in this case, the sample space is being represented as a list, right? H and T. All right. These brackets, right? It's not a normal parentheses. These are brackets. It is purposeful. It should be brackets. Brackets represent a set, right? The things within the brackets are the set of possibilities. I'm drawing a random sample of 1,523 adults for a survey question. The sample space contains all possible sets of responses from those 1,523 of the 235 million adults in the country. This S is extremely large and complex, and we cannot really represent that with a simple picture or a simple list. Okay, so this is just to illustrate that we can go from very simple two options to millions of options, depending on what we're doing, right? So we're going to look at an example. We're going to create a probability model for rolling a pair of dice, right? So I totally forgot to set this up properly. Oops. So give me a moment. All right, take three. All right, so we're going to have a sample space, S, and this is going to represent the outcomes of rolling two dice. All right, and I'm writing this with the notation. I've got my brackets, and I've just written in a sentence essentially what my set is. I could write out all the outcomes listed, but we're going to use a picture for that instead. So we're going to have a red dice, which can land on a 1, a 2, 3, 4, a 5, or a 6. We'll have a green dice, which could also land on a 1, a 2, a 3, 4, 5, or 6. All right? So this grid represents my sample space S. Now, in here, I essentially just fill in the different combinations based on what shows up on the dice. So our first entry here will have a 1 from red and a 1 from green. I should do these in better order. 1 from green, 1 from red. Right, the next one will have a 1 from green, but a 2 from red, and so on. And this allows us to easily make sure we don't skip anything, right? And fill in all the possible different outcomes of rolling 2 dice, right? I have my sample space representing all the different possible rolls when you roll 2 dice, right? We do get that there are 6 possibilities from the red dice times 6 possibilities from the green dice. Gives us 36 possible outcomes. Each outcome is equally likely. That's important. Right? This allows us to use the table accurately. Each of these outcomes has a 1 in 36 chance of happening. Right? Rolling a green one with a red one has a probability of 1 in 36. Right? So that means as I add things up, they just keep adding how much of 36 I have by adding the number of things possible. So for example, let's say I wanted to know what's the probability, or what are the chances of the sum of my 2 dice being less than 5. All right, so I want the probability or chances, the sum of the 2 dice is less than 5. All right, so I'm gonna go through here and I say, well, 1 plus 1 is 2, 1 and 2 is 3, those ones qualify, 2 and 2 is 4, 1 and 3 is 4, 3 and 1 is 4. This next, like, diagonal, 4 and 1, 3 and 2, 2 and 3, 1 and 4 are equal to 5. They don't count. I want less than 5. All right. So then my probability, or the area, so to say, of my sample space, or of my event, as we'll come to know it, is in here. And I have 5 possibilities, 5 outcomes that satisfy this question. All right, so the chances are 5 out of 36. Oh, 6. I can add. Man, why don't you guys tell me I'm making mistakes today? Jeez. Sorry, guys. Perfect. All right, hey, there we go. 6 out of 36. I can count. There's 6 boxes in my shaded area. All right. This is how we can use our area, kind of area model, or our probability model, right? Our sample space. What can I clarify now that I like royally mapped and fixed it? Okay. All right. So then, let's look back into our presentation. We have that. That sample space will be part of the notes that will be uploaded to Canvas. This is another way of demonstrating the sample space using pictures. This would take a long time to draw, which is why we have alternate ways of representing this, which take less time, such as what I drew in OneNote. All right, so here's another model for rolling a paired dice and the possible outcomes. All right. So this probability model allows us to not only see all the outcomes, but we can also find the probability of any collection of outcomes, which is called an event. All right. If A is an event, then its probability is written as P of A, right? P parentheses A, right? We use the letter P because P is the first letter in the word probability. Mathematicians are very creative. And so here we have the textbook definition for an event. An event is any collection of outcomes from some chance process. That is, an event is a subset of the sample space. Events are usually designated by capital letters like A, B, C, and so on. All right. So an important thing here is that an event is a subset of the sample space. All right. A subset can be the entire sample space. It can also be none of the sample space. There are events that have probability 0, and there's events that have probability of 1. Remember, our probability is always measured between 0 and 1. 0 being no chance, 1 being 100% chance. All right? So just because something can't occur in your sample space doesn't mean it's not a subset of the sample space. And just because something always occurs 100% of the time of your sample space, that's still a subset. Just want to make that clear. All right. Can you raise your hand if you need a moment to write any of this down? Okay. Let's explore another example. Let event A be defined as the sum of the two dice is 5. Let event B be defined as the sum of the two dice is not 5. What is the probability of A? And what is the probability of B? All right. So for the probability of A, we see that there are 1, 2, 3, 4 outcomes where the dice have a sum of 5. Since there are 36 possible outcomes, we get that P of A is equal to 4 out of 36, which we could reduce down to 1/9 or even display as a decimal, which would be a rounded off decimal of 0.11. In probability, it's kind of more typical to leave it as 4 out of 36 because the 36 has significance. It represents the total possible things that could happen, total number of outcomes possible, all right? And the 4 says, well, I have 4 of these events, 4 of these outcomes that fit my event, okay? And so the numbers have significance. So it's more typical to leave this as a 4 out of 36 than to reduce it or to do the decimal, unless it's something really nice that we know we're not going to lose accuracy by rounding to. Okay. And then the other part, what is the probability of B? Well, because the sum of the two dice not being 5 is everything else in our set, right? Then the probability of A plus the probability of B has to be 1. Because between those two things, we've covered all of the possible sums. So the probability of B is 1 minus the probability of A, which is 1 minus 4 out of 36, which gives us 32 of 36, which we could, again, can reduce to 8/9, but it is more better to leave it as 32 out of 36 because the numbers have significance. All right. What questions do you have? Does anyone need a moment to write any of this down? So now we have some basic rules for probability. The first, the probability of any event is a number between 0 and 1, which again fits our definition of probability. All possible outcomes together must have probabilities that add up to 1. All right? So even in our rolling the dice sample space, if we added up all of those boxes, 1 out of 36, we'd get 36 out of 36. Has to add up to 1. If all outcomes in the sample space are equally likely, the probability that event A occurs can be found using the formula P of A equals the number of outcomes corresponding to event A divided by the total number of outcomes in the sample space. This formula works when all the outcomes are equally likely. You need to see that statement. Each outcome is equally likely. Right? Then the formula works. There's other formulas you must that can be used when things are not equally likely. There's other strategies. The probability that an event does not occur is 1 minus the probability that the event does occur. If A is the event, then not A is when the event does not occur. Right? Just like our example on the previous slide, where we said the sum of the 2 dice is 5, and then the other event was the sum of the 2 dice is not 5. Right? We refer to this event as the complement of A and denote it as A superscript C. You know, like the C goes in the exponent spot. Okay? The idea of a complement shouldn't be totally new. We've used the idea of a complement in geometry, that you have complementary angles. It's whatever angle finishes, right, the line. It's the other part that we know it always adds up to. Please don't ask me if it's the 90 degree or the 180 degree one, because I always forget which one is complementary and supplementary. I always have to look it up when I teach it. It's just one of those things that never stuck. So, sorry. I think it's the 90 degree one. I'm talking about geometry, but I always have to check. Anyhow, as far as this is concerned, the complement of an event is the other things that could happen besides that event. Right? And lastly, number 5, if 2 events have no outcomes in common, probabilities that one or the other occurs is the sum of their individual probabilities. When 2 events have no outcomes in common, we refer to them as mutually exclusive or disjoint. Okay? So again, the probability that one or the other occurs is the sum of their individual probabilities when they are mutually exclusive or disjoint. All right? So we need a moment to write these down. We have some notation looking stuff that goes along with those same 5 rules. All right. For any event A, probability of A is between 0 and 1. That's what this means. This is our inequality that shows the P of A is greater than or equal to 0, but less than or equal to 1. If S is the sample space in a probability model, then the probability of S is 1. Right? It's saying, what's the probability of all of these things? One of these things happening. Right? 100%. You're going to get one of the possibilities within your sample space. In the case of equally likely outcomes, probability of A, the number of outcomes corresponding to event A over the total number of outcomes in the sample space. We have the complement rule. The probability of the complement of A is equal to 1 minus the probability of A. And the addition rule for mutually exclusive events, if A and B are mutually exclusive, the probability of A or B equals probability of A plus the probability of B. I want to stress the word or. In mathematics, or in the very least, we'll say in probability, and in other areas of mathematics, or is inclusive. This means that if you see the statement, you can have A or B. That means if anything in either of those events occurs, you've satisfied the equation or the requirement, right? So we look at the chances of any of those things happening, and that's the probability. If you see the word and, that is exclusive. I want to know the probability of A and B happening. I have to look at the things that occur in both events. What do they have in common? The outcomes that those events have in common satisfies the probability of A and B. There's a distinct difference between using the word or and using the word and when it comes to probability and in many other areas of mathematics. Okay? You have to be on the lookout for those. Any questions, comments, concerns? Do we need a moment to write any of this down? All right. So then, we're going to do some practice. All right. We're going to do a little Pear Deck here to practice probabilities using a sample space. So we got our basic probability Pear Deck. Woo. Here's our first question. Use the dice sample space below to determine the probability. You're going to use the same sample space for all the questions. So what is the probability that the sum of the two dice is 7? See what the answer should be. Lots of responses. Boom. All right. So based on the sample space and the possible outcomes of rolling two dice, 6 of the 36 possible outcomes have a sum of 7. And we see that running through this diagonal here. We have 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, and 1 and 6. Okay. And so the answer is a fraction between 0 and 1, right? 6 out of 36 is definitely less than 1 or greater than 0. And we've left the over 36 because that's the number of possible outcomes with 6 because that's how many times we had a sum of 7. Any questions? Anything I can clarify? Okay. What is the probability that the sum of the two dice is 7 or the sum of the two dice is 5? Again, find all the possible outcomes that has a sum of 7 or have a sum of 5 and add them up. All right. Here we go. The solution. The probability that the sum is 7 or the sum is 5 is 10 out of 36. There are 10 possible outcomes that satisfy that event, right? We can have 4 and 1, 3 and 2, 2 and 3, 1 and 4, 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6, right? These are all the possible rolls of the dice that have a sum of 7 or a sum of 5. Right, so this is the addition rule when you have mutually exclusive or disjoint events. Next, what is the probability that the sum is 7 and the sum is 5? when you roll 2 dice. In other words, how many different ways can you roll 2 dice where their sum is 7 and their sum is 5 at the same time? So let's look at the answer to this, and then I'm going to show you guys another visual to kind of help with this concept. So the probability that the sum is 7 and the sum is 5 is 0. There is no combination of 2 dice where their sum can be 7 and their sum can be 5 at the same time, right? This is because these events are disjoint or mutually exclusive. They have nothing in common separately, all right? So what that means is if we consider a sample space, right, let's say that this box represents my sample space S. And then I have event A and event B. Let's even say I have another event. We'll call this one C. And I have these circles, the red circles here represent possible outcomes. So this is my entire sample space. All right, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I have 25 possible outcomes. Right. The probability of A is 1, 2, 3, 4, 5, 6. Right, we have 6 out of 25. Probability of B, 2, 3, 4, 5, 6, 7, 8, 9. Right. We have the probability of A or B. Right. A and B are disjoint, and we can visually see that because they don't, the circles of those events don't cross, right? They don't share any red circles, red dots, right? A and C share some, B and C share some, right? But A and B share no little dots. So they are mutually exclusive, they're disjoint. So the probability of A or B is 9 plus 6, right? We get 15 out of 25, right? The probability of A and B will be 0. And this again is because they share no common circles. They share no common data, all right? If I wanted to say, okay, A, right, A and C have common data points, 2 of them. So that's going to be 2 out of 25. Right? So and represents that they have shared outcomes within their event space. Or is just saying how many possible outcomes exist within the 2 events. Does that make sense? Does this help clarify the difference between or and?
Can you repeat what you said, please?
Yeah. So when you're looking at and, probability of one event and another event, it wants to know what outcomes do those two events have in common. Right? So in the case of A and C, they have these two outcomes, right, that we can see as like the Venn diagram intersection in common. So we have a probability of 2 out of 25. Or wants to know what are all the possible outcomes between the two events, right? Could say, what's the probability C? And that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? And that's because between those two events, there's 11 possible outcomes. Okay? So and or has significantly different meaning. You have to pay attention to the words that show up when you're asked about probability. What other questions do you have? So hopefully that helps clarify a little bit with probabilities and sample space and how and or work. We're going to jump back to our Pear Deck. I have one more question, I believe, in there. All right. So right here, what is the probability that the sum is not 7 or 5? So I'm looking for the complement of the probability that the sum is 7 or 5. Let's look at the answer. So the probability that the sum is not 7 or 5 is the complement to the sum being 7 or 5. So we use the complement rule, right, for disjoint sets. And that is 1 minus the probability that the sum is 7 or 5, which was 10 out of 36, which we found earlier. And that will be 26 out of 36. So that means there's 26 possible combinations of dice, 2 dice, where their sum is not 7 or 5. Okay? It's all the other options, essentially. Any questions about this last one? So that's a great question. So Lolly's asking, do we always have to use 1? In this situation, would it be appropriate to write 36 over 36 minus 10 over 36? Yeah, that's totally fine to write it as 36 over 36 minus 10 out of 36. 36 out of 36 is 1. When writing rule, right, when we write down the rule for this type of calculation, we just use the number 1 because we know that no matter what it is, the number I'm subtracting from is going to be equivalent to 1, which, you know, in this case was 36 over 36. Using 36 over 36 in this case is a little easier because you can do the subtraction of fractions with a common denominator and that kind of stuff. So it does make it a little simpler to see what's going on as far as the math. So there's a very long answer to say if you're using 36 over 36, yes, that's fine, because it's the same as using 1. So hopefully that wasn't confusing. Any other questions? Nope. All right, so then last thing, we end that. So a quick look at Canvas. Here is week 13. We're in Tuesday. We just went over part of section 5.2. We'll finish 5.2 on Thursday. Looking at probability rules. The live class resources will be updated with everything we did today and the video recording. And then the discussion board for today will be probability models and basic rules. All right. And here it is. The scenario, we have two events being talked about. We're going to choose an American adult at random to find two events. A, the event is the person has a cholesterol level of 240 milligrams per deciliter of blood or above, high cholesterol. B is the person has a cholesterol level of 200 to 239 milligrams per deciliter, borderline high cholesterol. According to the American Heart Association, the probability of event A is 0.16, probability of event B is 0.29. Explain why these are mutually exclusive, what the event A or B is, right? What is probability of A or B? And if C is the event that the person chosen has normal cholesterol below 200 milligrams per deciliter, what is the probability of C? So this is based on what we did today in class as far as basic understanding of probability rules. If you do have any questions, please let me know. You can email me. You can ask me right now for clarification. Other than that, that's the lesson, guys. That's everything.